Okay, hello everyone. So today's feature review is actually going to be via video. We had a text post all prepared and ready to go. Unfortunately, it was a few thousand words and many pages of diagrams and schematics and all sorts of crazy stuff like that. So it all just sort of became a little bit difficult to digest. So we're going to take a little bit of a break from that format for this one. And if this is something you guys enjoy and you like, feel free to let me know. Just send us a message on Discord or lob a comment in the YouTube comment section, and perhaps the next few that we do will be just like this one. But moving on to what we're going to be talking about today. So we're going to cover the pneumatic system simulation on board our Fenix A320. So it's a little bit of a tricky one to cover because, personally speaking, I often want to start diving quite deeply into the design and engineering that went into the rail airplane because it is some pretty fascinating stuff. But for now, I will relegate myself to talking about how we've recreated these systems. So very similarly to the hydraulic systems and subsystems, everything in the pneumatic simulation has been physically modeled. So what you end up with inside your Fenix A320 is a complex physical air mass simulation. And this air mass simulation is driven by and interacts with the correct and relevant mechanical components and control computers. So this has allowed us to really push for some really high levels of detail with what we've been able to do with the entire pneumatic system. Now, today we're not going to talk about the whole thing. We'll pick out a few subsystems that will help me illustrate the point of what we're actually trying to do and what we've achieved. And hopefully that will be enough to give you a really good picture of what's going on throughout the entire airplane. So we'll start with the basics. We're going to talk about some bleed air first. Okay, and you see a nice little ECAM synoptic right here. I'm going to bring up a little diagram. So I'm going to get started with the diagrams already. So here's a simple diagram of what goes on, to tap some bleed air out of the engines. So it's introduced into the A320's pneumatic system. So bleed air, that is introduced into the A320's pneumatic system from two compressor ports in each engine. Now, the first one bleeds air from the intermediate pressure stage of the compressor, and the second bleeds air from the high pressure stage of the compressor. Now, the airplane prefers and defaults to feeding from the intermediate pressure stage. However, there are certain cases, like right now, where the airplane is at idle, or the engines are at idle, and the intermediate pressure stage is insufficient. And that necessitates this high pressure valve right here. This necessitates this high pressure valve opening and supplementing the pressure regulation process by also feeding from the high pressure stage. This entire process and this valve is controlled by the bleed monitoring computers. So there's two of them, one for each engine. These are semi-redundant. We'll get to talking about them a little bit later. I'll fail them and you can see what happens. But for the moment, they're semi-redundant. So should one fail, the other can take over some of the responsibility of the opposite side. Now, with this design, what you're going to look for and what I'm going to show you is the bleed management computers ordering the high pressure valve to open and close depending on how much pressure the intermediate stage of the compressor is able to provide. So this, of course, is tied into the speed of the engine itself. So if you leave the engine at idle, the BMC will request the high pressure valve to open. Start adding thrust, and eventually you'll see the BMC will order the valve to close because the intermediate pressure stage is providing sufficient pressure to the bleed air system. So it's supplying the bleed air system just fine on its own. So we'll just take a look at that right here. So as you can see, we're sitting at idle. So idle N1. And you can see here that the valve is open and the high pressure port is supplying the bleed air system with some pressure. Now, if we increase the N1 and we start adding some thrust, you'll see the BMC will command these valves to close because the intermediate pressure stage is able to provide what we need to power the bleed air system. So I'm going to bring the N1 up in just a sec. So put some power in. There we go. So there's a bunch of N1, and you'll see it immediately goes amber, and it has basically said, okay, we've got more than enough from the intermediate pressure stage. We don't need any of the high pressure stuff. So we're going to close that valve off, and we're going to leave it be for the minute. And then the moment we bring the thrust back to idle, you can see there that the valve, the BMC, has basically said, okay, we now need more pressure in the system. So let's open up the high pressure valve, and we'll start feeding the bleed air system from the high pressure valve as well, so that we can get a little bit more pressure in there. So it's a really smart system, and that's the BMC's job there, is to ensure that there's a minimum amount of pressure in the bleed air system, and it does so by regulating these valves. Now, of course, there are some more fairly complex situations in which this valve will open and close and whatnot, failures, etc. All of this stuff is covered, and if you do want to dive into some of the documentation, I would highly recommend what I'm using here. So this is from smartcockpit.com. They have a lot of documentation. It's all for free, so feel free to head on down there and have a look at whatever you want to, and you should be able to mess with the same stuff on the Fenix A320. But we'll just move just a little bit past the pressure. So we've talked about how it regulates pressure, but then there's the next part of this, where it also regulates temperature. So all of the bleed air coming in from the IP and HP stages of the compressor is not only incredibly hot, but the temperature also varies significantly depending on the thrust setting of the aircraft. Now, this is courtesy of Adiabatic Heating. Adiabatic Heating is modeled in our air mass simulation, so I'll talk about it in just a sec. But Airbus decided that the best temperature for bleed air entering the packs is 200 degrees Celsius. So therefore, it regulates the system as best it can to 200 degrees Celsius, as you see here. Now, it does this through something called the fan air system. Now, the fan air system is depicted here. So you can see this is the fan air valve, or the fan air system, which makes use of a pre-cooler and a fan air valve. So if we just jump to the outside of the airplane for a second. So as pressure changes in the IP and HP stage, and that's down here. So if you want to kind of visualize what we're looking at, the IP stage would be somewhere around here, and the HP stage would be somewhere around there. So this is the compression chamber and whatnot. So these stages are in here. And as pressure changes in the IP and the HP stage, so it increases when you add thrust, the valves for the fan air system will open and close as the temperature increases because of adiabatic heating. So adiabatic heating, for those of you that don't know, very basically put, it's the adiabatic compression of a gas which causes a rise in the temperature of the gas. So adiabatic heating occurs when the pressure of a gas is increased by work done on it by its surroundings. So, for example, a compression chamber, exactly kind of what we're talking about here. So what you have with this fan air system is actually quite fascinating. You have a little port in the shroud, there's a low pressure stream of air that comes from inside the fan shroud. Now, this is before the compression chamber, so it's some really nice, cool air. And this air comes up into this area right here. So I know a lot of you have probably looked at the engines on an A320 and gone, what is that on the top with these vents? What is it venting out there? Well, that is where the pre-cooler resides. So Airbus specifically call it a pre-cooler. Now, this is really just an air-to-air heat exchanger. So it brings two air streams of different temperatures into thermal contact. So essentially, you're looking at the IP and HP bleed air being sent up this way, and you've got nice cool air from the engine shroud coming up this way. And all the excess is then vented up this way, and kind of you get nice 200 degrees Celsius air going into the airplane. So there's a valve that controls this, and you can see that valve right here. So this is the fan air valve, which then regulates the temperature. So the temperature sensor for this is actually up here. Now we've modeled this. This documentation is a little bit simpler, so it's not really a technical document, but there's a temperature sensor right here, which makes sure that air leaving this pre-cooler area is at 200 degrees Celsius. So this feeds back into the fan air valve, and that controls how it opens and closes, of course, all handled by the bleed management computer. So if you can kind of imagine these two streams of air colliding in such a way that the output is 200 degrees Celsius, you're basically pretty much there. So we can demonstrate this to you. So if we just head into the airplane, and I'm very sorry if I sound a little hoarse. It's been a whole day of trying to record this video. We're on take 648. Not really, but it feels like it. So, right. So if we increase thrust, right, you will see here that the temperature will briefly rise. So the BMC will regulate the temperature to 200 degrees Celsius plus or minus 15 degrees. Now, this is a reactive system, not a proactive system. So you will see that as I increase thrust and you get a sudden surge of adiabatic heating, and you know the temperature rises from the IP and the HP ports, that it takes a second. The temperature will rise by about 10-15 degrees, and then it'll come straight back down again as the valve opens, because there needs to be some delay. There needs to be some time for the valve to open and for it to then regulate the temperature down. So if we increase the thrust, you will see here, you're looking at these two readouts right here. So up comes the thrust, and we've just sent it straight up. So it goes up to about 210. So you can see the HP valve has disconnected, doesn't need it anymore, but it's come up to 210, and now the valve is, again, it's opening, and it's regulating itself back down to 200. So the valve is not it's not a yes, no, it's not a bool, it's just, it can kind of open as much or as little as it needs to. So it's not just open or close. So if we bring it down again, you'll see the temperature will dive just a little bit. So it'll probably come down to about 190 before the valves then start closing and then regulating the temperature back up to 100. So it brings less cool air into the equation, and therefore the temperature comes back up just a little bit. So there you go. It should be coming back up to about 200. So the point of modeling these systems in kind of physical detail, and the reason why that literal kind of valve is modeled to open between kind of, you know, all of its possible stages, is because then you end up getting the behaviors that you would expect out of an A320 when you put it in some weird situations. Now, if we go to the weather menu, now this is a pretty well-known fact about A320s, but if I bring this temperature down quite a lot, it's known that the pre-cooler is not going to be able to maintain 200 degrees Celsius because the outside air is simply too cold. So the compression chamber is obviously taking in air from the outside, so the engine is sucking in air from the outside, goes into the compression chamber, it heats up a lot, but it doesn't heat up enough. So right now we've got air coming in from IP and HP that is north of 200 degrees Celsius. But what happens if the actual compression itself leaves us with air coming in that is lower than 200 degrees Celsius? So if we just bring this down to about minus 15. So what it's probably doing right now is that it's jammed the valves closed, and it's gone, you know, this is really cold. We're not getting the temperature we need. I need this to be at 200, but it's not. So you can see that the temperature is diving and the pre-cooler is not able to maintain 200 degrees Celsius. So it's modeled that the temperature that comes in is based on, of course, the outside air temperature and the N2 rotation of the engine. So we have basically modeled this so that when you go to somewhere really cold and it's minus 10, your pre-coolers are not going to be able to maintain the temperature that they should. And this happens in real A320s as well. Now, if you go to Siberia for whatever reason, and I put the temperature down to minus 29 and it starts getting really cold, you'll see that the pre-cooler then drops down to 145, and it goes into an amber color. And you would think that that is, cause for some concern, but it isn't. It's not the worst thing in the world. It doesn't damage the packs. They just simply get a lower input temperature, but it doesn't damage them. It simply adjusts for this lower air temperature coming into the system. So you will see that here you've got still a nice 20 degrees coming out of the pack. So no problems for the pack system there. You would expect something like this to generate an ECAM memo, but it's a bit of an interesting one. There are some very specific conditions under which this warning would generate an ECAM memo. So essentially it will only give you an ECAM warning, not memo, but ECAM warning, unless the wing anti-ice switch is on and the aircraft is in the air. So if you're not in the air and not using wing anti-ice, it's not going to give you an ECAM warning. And this is purely because it taps out some of this air right here for the wing anti-ice. So this nice 200 degrees Celsius air is coming out, and it's heating up your leading edge of your wing. So it's obviously a cause for concern when this temperature is not where it needs to be. So this is when you would get a little bit of an ECAM memo. But if I bring, again, you can see the effects of the modeling of the adiabatic heating, because if I bring the thrust up again, you will start seeing the temperature start to rise a little bit. And you can actually see the packs start to self-regulate and close their valve just a little bit so that they can maintain that 20 degrees Celsius output. So we'll drop the thrust and we'll put ourselves back on planet Earth with 16 degree outside temperature, which should be nice and just about right. So the next thing that I'd like to show you is in the failures menu. So let's close this for a second and we'll bring up the failures menu. Pneumatic, and we'll head on down. So what I can show you now is failing the pre-cooler temperature sensor. So of course this pre-cooler is regulating, the pre-cooler is not this pre-cooler, but the pre-cooler is regulating this temperature right here based on its temperature sensor, the one that I told you about. So if we bring up this diagram right here, so there is a temperature sensor right here. And this temperature sensor right here is giving you this readout. Now, these readouts are not what we're about to fail. We're about to fail the actual temperature sensor on the pre-cooler, and we're going to give it a false high temperature reading. So this sensor is not something any of you will ever be able to see because it's not provided as a readout on any of the ECAMs, but it does exist in the background, and that's the case for a lot of this stuff. So I'm going to fail on engine 1. And what you're going to see here and what you're really looking for is essentially we get a false high temperature reading. So the valve is going to open itself fully and it will stay open fully. And that's kind of what we've got there. So there you go. So no ECAM warning unless the wing anti-ice switch is on and the aircraft is in the air, of course. So again, the same thing as when we had some really cold temperatures earlier. So you've now got the valve is completely open, and we've got no ECAM warning, nothing, and we've got a false high temperature reading. So you can see the cause and effect there of this false high temperature reading. It really goes to show kind of that valve is acting on information that it gets from a temperature sensor, much like the rail aircraft's valve is reacting to information that it gets from the temperature sensor. Same thing. So let's unfail that. That's definitely a word. Unfail is definitely a word. So let's let that come back up. So as we kind of fix the temperature sensor, it actually realized what the real temperature was, and it then started closing the valve so that we could get a bit more heat in, and then it starts to slowly open the valve as we come back up towards 200 degrees Celsius. There you go. So on to the BMCs. So these are the bleed monitoring computers. So we talked about them a little bit earlier. So if I go ahead and fail BMC2, it will tell you bleed monitoring system 2 fault. However, you still get your readouts for the number 2 engine. And this is because BMC1, like I said, they're semi-redundant. BMC1 has now taken over some of the duties of BMC2. If you fail them both, now you have a pretty serious problem. So everything's ambered out, and it gives you bleed monitoring fault. And in a second here, you should get some more ECOM warnings. There you go. And generally, this is probably not a great situation to find yourself in. So we'll unfail those again. So I think that just about gives you a good idea of kind of how we're modeling air coming into the actual airplane itself, and the level of detail that we're going through there. Of course, this extends out to kind of every facet of the bleed air system, you know, down to the wing anti-ice and things like that. But unfortunately, we don't have the time to cover absolutely all of it today. So hopefully this gives you a good idea. So we'll move on now to the packs. More specifically, we'll talk about the packs in the air conditioning system. So for those of you that don't know, packs, PACKS, pneumatic air conditioning kit, or pressurization air conditioning kit, depending on who you ask. So I've got a little diagram for you. Again, more diagrams, lots of fun. So it's kind of a follow-on from this one. So you can see, like I told you, we got nice 200 degrees Celsius air now coming out of here as a result of this pre-cooler doing its job and this fan air valve regulating the temperature nicely. So we've got 200 degrees Celsius air coming up here. And if we move over to our pack diagram, you can see here. So now we've got 200 degrees Celsius air coming up this way. And that then goes into the packs. So from the packs, it cools it down. Right, so I'll talk about specifically how the packs do that, but for now it cools it down and it moves this air into this mixing unit, and this mixing unit is essentially a giant bucket of air that the airplane will then distribute to various places. So the mixing unit is pretty cool. You have recirculated cabin air coming into the mixing unit as well from these two fans. So it basically brings in cabin air, recycles it, puts it through a filter, and then dumps it in the mixing unit to be redistributed once again. Now, this is something that aircraft designers like to do because bleed air is expensive and the engines don't like it if you tap too much air out of them. So aircraft designers will generally do their best to limit the amount of air that they bleed from the engines. Hence, we recycle a little bit of cabin air. Now these cabin air fans, they can actually be turned off. So there's a button on the overhead, on the ventilation panel, that'll let you turn off these cabin fans. Let's see if we can, there you go. So cabin fans. So on a Boeing, this is called a recirculation fans. Here on an Airbus, it's called cabin fans. If we push that and we move into the conditioning page, you can see we get a little amber notification here that our recirculation fans or our cabin fans are switched off. I'm going to turn them back on again, but I'll use these a little bit later to demonstrate something else that we've done. So if we go back to the diagram, there we go. So pretty cool stuff. So you can turn off the cabin fans, of course. So if we've inhibited these fans, the system will run only off of bleed air. So you're not getting supply from anywhere other than the bleed air, unless you've got ground, air plugged in, whatever. But we're not talking about that right now. So again, you'll only be working from the bleed air, no cabin air. So we'll move on to talking about what actually goes on in the packs. We'll come back to the mixing unit in a moment. But we'll talk about what actually goes on in the packs to give you that cool air that goes into this mixing unit. So here is what's called an ACM. So it's called an air cycle machine. This is what gives you your cold air. So it takes that 200 degrees Celsius air that comes in and it generates 20 degrees Celsius air. When I was much, much younger, I always wondered where the air conditioning system on an airplane is. Well, it doesn't have an air conditioning system. This is actually an incredible piece of design that doesn't rely on any electricity whatsoever to cool this air down, just physics. And it's, you know, it's one of those things. I'm not going to segue off too hard, but it's super cool. So I'll give you some terms later if you want to go ahead and Google those to learn about how it works. But essentially, it's part of the packs. It's responsible for cooling the air used in the air conditioning. So we have a system that comprises here of a couple of heat exchangers and an expansion turbine. So you've got these two heat exchangers right here, and you've got an expansion turbine. That's what this little thing here is called. So you've got your nice 200 degrees Celsius air coming in here, and it goes through this heat exchanger, this first heat exchanger. Now, this heat exchanger works pretty similarly to the heat exchangers that we talked about earlier. So you've got your air and it comes through here, and then this air goes through this this compressor. Now, I could segue off into the expansion turbine and its physics. Essentially, it uses an isentropic process. I'm not gonna turn this into a physics lecture. It uses an isentropic process to leave you with nice cool air coming out of your pack outlets. So if you want to learn more about this, just Google expansion turbine isentropic process. It'll give you everything you need. But for now, we'll just go ahead with magic happens here, and you get cool air coming out of the other side. So first heat exchanger through the compressor, second heat exchanger, and then you've got some really nice air, nice cool air coming out, courtesy of the exhaust from the turbine. So we have here a ram air inlet flap. Now this is something I can physically show you in just a moment. These heat exchangers work similarly to the air-to-air heat exchangers that we were talking about earlier, and they have to bring in air from somewhere, nice cold air from somewhere. So again, how in the first instance, when we were talking about the fan air system, it brought in cold air from the engine shroud. Well, the packs bring in cold air from the belly of the airplane with this ram air inlet flap. So let me just go ahead and show you that. Oh, I'm going to have to connect my Xbox controller to move around. So just bear with me for 1 second. There we go. Lovely. It's a lot of talking, isn't it? Right, so here are your ram air inlet flaps. Two of them. One for each pack. So you've got these two right here. There you go. So interesting development anecdote. I'll share that with you in just a second, but we'll talk about really quickly how these work. So of course there's a bunch of air that's rammed into these when the airplane is flying along, and it's a bit of an interesting one because if you look at the diagram, you'll see that it is really quite a delicate system up here. And you don't really want some foreign object debris to come flying in here and destroy a bunch of ducting and whatnot. Given that it's on the belly of the airplane, Airbus naturally had to think about this. So what this ram air duct does is that it actually closes under very specific instances, the ram air inlet flaps. So if I give it toga power right now, you will see that these ram air inlet flaps will close. They'll close very slightly, not a lot, but enough to dissuade any errant foreign object debris from entering this area of the airplane. So if I just ram it into toga power, there you can see the flaps just closed ever so slightly. And if I bring it back out again, you should see them start to slowly open up again. So this is again assuming that the airplane has now taken flight. So of course it's a combination of things like the weight on wheels, so the LGCIUs and kind of the toga power and whatnot, for the airplane to basically use its brain and think about whether or not it's on the runway and it needs to close these flaps. I'm not going to dive way too deeply into these details because, you know, we've got all of this documentation and we've done all of this work. We're not going to give all of it just away just yet. But there you go. So you've got this really cool system that's sitting there protecting this essentially this process, this ACM right here. So there you go. So you've got this nice cool air that comes out of the outlet, and you can see what exactly it's telling you. So right now on our current airplane, if we look, our pack outlets are telling us that we're doing 20 degrees Celsius out of here. So if we just, oh, I don't know how we're going to do this. This is going to be quite challenging, actually. So there we go. Right. So it's essentially telling us right now that at this location in the process, so if you look at this location, so after it's gone through the first heat exchanger and it's gone through the first compression cycle, it's at 115 degrees. And then it passes through the second heat exchanger, and as it comes out the other end, it's at 20 degrees. So it's, again, it's doing all of this without electricity. Really cool stuff. And we've modeled all of this kind of stuff right down to the ram air inlet flaps opening and closing. So the interesting development anecdote that I wanted to share with you was actually about these ram air inlets. So when we first designed this, like I mentioned, it's a physically modeled system. So when we started closing off this ram air inlet, and in fact, when the airplane was sitting on the ground for a while there, something was missing. We were wondering why constantly we were getting overheats and whatnot. It was only upon diving into some pretty obscure documentation that we realized that there is actually a fan in there, and that fan helps kind of generate air, suck air in through these ram air inlets when the airplane needs to, it needs to bring some air through this duct right here for these heat exchangers. So there's a little fan here, and it's not documented. But again, because it was a physical simulation, the air coming through here was just not cool enough. There wasn't enough air coming through here. So we were getting a bunch of overheats and all sorts of crazy stuff. Until we realized that there's a fan in there, and the diameter of the fan and whatnot that is pushing the air through this ducting, and how wide this ducting is and whatnot, that we could then take that away and go, okay, the system now works as it should. So it's just an example of kind of the level of detail, and again, the physical simulation that we've gone through and the lengths that we've gone through to create this. So just diving back into the airplane in a second when I can figure out what I need to hit to actually get into the airplane. There we go. So we'll move now into talking about the mixing unit. So if you look at this bleed air synoptic, these three little arrows right here, these are telling us that we've got 20 degrees Celsius of air going into the mixing unit. So if I bring up the documentation once again, you will see that upon scrolling up, we've got a mixing unit right here. So let me see if I can put this in a way that makes sense. There you go. So you've got your mixing unit here. So out of the packs, so the packs are down there, right? Out of the packs into the mixer unit right here. So this mixer unit, now it's a bit of an interesting one because it's like a massive bucket of air. So the airplane will now take this massive bucket of air and it will distribute it to the various zones that need air. So the A320 is split into 3 or 4 zones depending on how you have the airplane optioned. So you've got the cockpit, you've got the forward compartment, and you've got the aft compartment. Now, it's a bit of an interesting one because you can request different temperatures for the forward, the aft, and the cockpit all at the same time. And it leads you to wonder, from this mixing unit, which presumably is one temperature, how do they regulate the temperature for other areas of the airplane? So essentially, the mixing unit will be at the lowest temperature, or the lowest requested temperature across the 3 zones. So if you've got 25 degrees for the forward, 25 degrees for the cockpit, but 20 degrees for the aft, inside this mixing unit, it's going to be 20 degrees. Okay? And what it then does is that it sends this 20 degrees up to the aft, and it sends 20 degrees towards the forward, and it sends 20 degrees towards the cockpit. And then it uses these trim air valves. And these trim air valves are powered or supplied from that nice 200 degrees Celsius air that I was talking about much earlier. Now, before they hit the packs, they actually tap off some of this air and they send it to these trim air valves. So this 20 degrees Celsius coming up this way is then met by a little bit of hot air, 200 degrees Celsius air, just the tiniest fraction of it, enough to cool or heat this to 25 degrees. So you get 25 degrees coming out of the forward and the cockpit compartments. It's a really cool system. Really, really cool system. And we've modeled it. So I want to run through a couple of things that'll hopefully show you this. So just a second. Let's close this off. So now that you understand kind of vaguely how this works. Okay, so we'll bring up the air conditioning and we'll talk about this for just a second. So I've got the airplane empty right now. And the reason I have the airplane empty is because it will help me demonstrate the temperature changes better this way. So what we've done is that we've actually modeled having passengers in the back affecting the heating and the cooling rate of the cabin, because of course passengers and people will generate a heat output. So therefore it has to work a little harder in the forward and the aft cabin. However, you can actually see this modeling already working in the cockpit because we've got a lot of equipment in the cockpit generating a bunch of heat. So in the cockpit itself, we've requested a temperature of 24 degrees. It's currently 25 degrees. And the airplane is putting in 21 degrees of air into the cockpit. So the air blowing into the cockpit is blowing in at 21 degrees. The cockpit is at 25 degrees, and we've asked for it to be at 24. Now, the reason for this is because of all the equipment generating heat. So we've modeled that thermal property. So the system is always blowing air a little bit cooler than the rest of the zones, assuming they're empty, because of all of this heat these heat generating items. Sorry. Whew, we've been talking for a while now, haven't we? Okay, so because of all of these heat generating, all of this equipment generating this heat, so of course we've got to have this blowing a little bit colder just to maintain the temperature where we want it to be. So it's a bit of an interesting one. Of course, the thermodynamic properties of passengers and whatnot across the forward and the aft cabin, I've emptied it out just so you can see the changes much quicker, but the moment you put in some passengers, it becomes much slower to heat or to cool. So if we just really quickly demonstrate this. So if I go over to the overhead, and I'm going to go ahead and request a completely cold forward cabin. Now what we're going to see here is that this temp starts dropping. And if you remember across our bleed air, you'll see that was at 20. Now it's at 5. Okay. And this is gonna drip down to 5, or it would drip down to 5 if we didn't have these cabin fans. So the cabin fans are on right now, which is why there's a disconnect between here being 5 and here being 9. If we go ahead and turn off these cabin fans, you'll see this temperature will drop even more. So it drops down. Now it's giving us exactly what the pack is outputting. So the pack was outputting 5. It was going into the mixing tank, and then the mixing tank was recirculating some of this hot air from the cabin, which means that the temperature in the mixing tank goes up by just a couple of degrees because it's pulling in warm air from the cabin. But now it's not doing that because we've turned off these cabin fans. So we end up getting pretty much a direct one-to-one with what the pack is outputting and what you're seeing here as air coming out of the actual vent. So it's going back up again because it's coming down to the temperature it needs to be. So it starts automatically regulating that now. It's a really cool thing to see in practice. So we'll go ahead and turn on these cabin fans again, and you should start seeing this temperature climb a little bit faster than it normally would. Again, just a reminder, if we look at this, you've got this cabin air coming in. So it's going to make the heat in the mixing unit a little bit hotter. Of course, the trim air valve was completely closed so that you could get as cool air as possible through there. So you can see I've requested here on the Airbus, it's a little bit funny. The 12 o'clock position is 24 degrees all the way to the left, and cold is 18 all the way to the right, and hot is 30. So a little bit of an interesting one. So yeah, that's a pretty cool one. So you can sort of see how it moves its valves around just to keep that hot air where it needs to be, or to keep the temperature of the air where it needs to be. So the next thing to look at is what happens if you kill this hot air. So if we look here, we can actually close this valve. right? There's a button right here on the overhead, and I'll close that in just a moment. It will close off this valve, and then suddenly we will no longer have the ability to trim out or to use the trim valves to trim out the temperature going into the cabin. So let's set these to some different temperatures. We'll make that a bit hotter. We'll make that a bit colder. So we'll just set it a little bit wacky, and we'll give it just a moment to do what it needs to do. Okay, so you can see it's regulating the temperature. So what do you get when you take away its ability to regulate hot air? So we'll turn that off. So there you go. That's the button right there on the overhead. So we've turned off the hot air regulation. And what it's basically going to do now is that it's going to take an average of the requested temperature, and it's going to start blowing that through the packs. So you'll see here that your packs will start giving you 15 degrees out, and this is pretty much direct from pack to outflow, right? So you've got no trim air anymore. So your packs know this, because again, the entire system is physically modeled. So we know, right, that you no longer have the ability. That valve is closed. There's no more hot air coming through. So there's a little computer that'll basically tell the packs that, hey, you've got to start trimming the air out, because the packs can do that. It can trim the air out. You can see that the packs have their own valve. So it'll start giving you 15 degrees out this way, and you'll start getting 15 degrees blowing out. So you can see it averages out what you're requesting, and you can still maintain a nice comfortable temperature that way. It's a really fascinating system. So it's then of course reverted to the packs directly blowing air out into the cabin without any of the trim air working. Okay, so now we've seen the packs regulating temperature on their own. We'll just set it back to the way it should be, which is letting it do its trimming. So there you go. So it'll start trimming according to what you've requested, and we'll just set these back to relatively sane temperatures. There you go. And we'll watch it starts kind of trimming its way up. So again, those relatively sane temperatures, they should be around about, looking at that, so you've got 24, 18, so it'll be somewhere in between. And once it gets to where it needs to be, it should level itself out again. So we'll talk a little bit about cargo heating now. So to do that, what I'm going to do first is I'm going to bring up on the left MCDU, I'm going to bring up the packs and cargo page. So you can see here that we have cargo heating as an option. So all A320s will essentially blow cabin exhaust air into the aft cargo compartment as per normal. But with the heating option, you get a trim air valve like you do for the cabin, and that will help you regulate temperature in the cargo compartment. Now, this does mean that the lowest temperature that you can have in the cargo heated compartment is only as low as the lowest temperature, or the lowest temperature of the exhaust from the cabin, because this is cooling cabin exhaust air, or it's heating cabin exhaust air to maintain that comfortable temperature. So what this essentially means is, if you look at this, you've got 24 degrees and 23 degrees going into the cabin, and the cabin itself is 23 degrees. Now, there are no people in the cabin. If there were people in the cabin, you would see that this exhaust temperature that's going into this aft cargo compartment will probably be a degree or two higher. But right now, because there's no passengers, 23 degrees is the temperature in the cabin, so 23 degrees is the temperature of the cabin exhaust. This 23 degrees is being piped into the cargo compartment here. So if we were nice and high up and in the sky, you know, normally this would come down to maybe single digits or high teens or whatever, and this would help keep it nice and warm. Now it's sitting at 20, but it's blowing air in that's 23 degrees. So if we just heat up, for the purposes of demonstration, the cabin, you'll start seeing that this cabin temperature will rise. And as this cabin temperature rises, you'll see this exhaust gas, or this exhaust air essentially heating up as well. So that's now going up to 24, and this will now go up to 24 because it's again using exhaust air from the cabin to keep this cargo compartment where it needs to be. Now, another interesting thing about this, why is it not actually rising in temperature? Well, that's because you've got 8,000 kilograms of baggage in there and 8,000 kilograms of stuff in there. An empty room would definitely heat or cool much quicker than a room that's full. So if we go ahead and enter 0 into our cargo compartment, so now it's completely empty, you can see the temperature will begin to rise. It's all part of what we've done to make it so that these minute little details that people will generally never know about are all there, because it just makes it a better experience. So, so we've modeled the thermodynamic properties of cargo. So an empty hold versus a full hold with luggage will heat and cool differently, and whatnot. So again, it's all part of what we've done to really make this as in-depth as possible. I know some of you may look at this and go, well, what's the point? Well, for us, the point is that it's a bit of a labor of love, and it's a bit of a challenge to see how far we can push the boundaries with this. So that's exactly what we've done. And that's why, we can achieve these effects, because we've taken the step to basically simulate as much as possible the physical aspects of this entire system. So another fun thing that we can talk about really quickly before we wrap up, we will talk very, very quickly about these right here. So these are Avionics inlet, and then on the other side of the airplane, you've got the Avionics equipment outlet. So the Avionics ventilation inlet and outlet. These are kind of interesting. So let's just bring up the documentation for these for just a sec. Again, another one of these physically simulated things that I can actually show you, because all the rest of it is code. If I can find it, there you go. Okay, so this is the Avionics ventilation. It basically cools and heats the avionics bay under the flight deck. This is a lot, and we are running quite short in time because we've just blasted past 45 minutes on this video. So I will very, very quickly point out that these are currently sitting open. So open circuit configuration when the skin temperature is above the on-ground threshold. So plus 12 degrees. So that, we've modeled all of these bits here, but I'm just going to show you the one, just because it's the only physical one that I can show you. So you can see this open circuit. So it's open on both sides, but there's some logic as to whether or not it's open or closed. So if I go ahead and so if we look at the documentation really quickly, so we see on ground threshold plus 12 degrees temperature increasing, or plus 9 degrees temperature decreasing. So this is when it's open. But on ground operations, it closes when the skin temperature is beneath the on-ground threshold, so plus 12 or plus 9. So remember, that's not the air temperature, that's the temperature of the skin of the airplane. So we'll have to bring the temperature down quite significantly, but if we do, and it should start cooling, and there you go. So it then reverts to its closed circuit configuration. So if we then bring it up again, there you go. So, and then it opens up again. So it's all part of a greater system, and that's kind of what we tried to do with this. We tried to make it all part of a greater system so that these tiny little, bits of the airplane are all represented the way that they should be. I hope you enjoyed this. I'm gonna have to cut it off here because A, my voice is going, and B, I don't know how many of you are left here at 49 minutes after I've been hopping on about systems for, almost an hour. So I will leave you with this. I hope that all of you have a fantastic evening, And I hope that you enjoyed this quick little feature overview of feature review in this new format. Have a lovely, lovely day, everyone, and I'll see you next Friday.